Good evening, everyone, and welcome to the Amateur Radio General Class, session number 9. I'd like to take the opportunity and say I wish that everyone had a great series of holidays. In Trinidad and Tobago, we had Indian Arrival Day, as well as Corpus Christi just yesterday. And of course, our participants in the US, you had Memorial Day. So wish everyone had a great holiday and is well refreshed and relaxed. So our previous session, we went through our usual question and answer. We had a look at the question pool, relevant questions to the theory from the previous class. We looked at power supplies. We discussed the linear and switching power supplies. We had a look at rectifiers, rectifier circuits. We also dealt with filters using capacitors and inductors. We then looked at the switching mode power supply. We had a look at schematic diagrams. We then delved into digital circuits, followed by logic circuits and truth tables. We also looked at what the D flip-flop was, also the 3-bit counter, and we ended up with shift registers. So this is where we are in respect of our curriculum. We are hoping to complete practical circuits today. So progressing quite nicely. As usual, we recommend persons consider taking the practice exams to see where you are at with your knowledge. We did not have any questions from last class. So we now proceed to review the question pool material related to the theory that we would have dealt with last session. Okay, so let's go straight into the questions in the question pool. What portion of the AC cycle is converted to DC by a half-wave rectifier? So let's break that down. What are they asking us? What portion of the AC cycle? So the AC cycle is a sinusoidal wave from 0 degrees to 360 degrees. And they're asking a half-wave rectifier, not a full wave. So last class, we said for half-wave rectifiers, it only converts half of the cycle. So half of that 360-degree cycle is 180 degrees. Next question in the question pool. Similar question to the previous one. What portion of the AC cycle is converted to DC by a full-wave rectifier? So they're asking us now not about half wave, but full wave. And we said the full wave rectifier does the full cycle, which is 360 degrees, which is the answer. Next question in the question pool. What is an advantage of a half wave rectifier in a power supply? So let's break that question down. What are they asking us? They're asking for an advantage. But an advantage of what? For a power supply, the use of a half-wave rectifier. And if you recall, we went through the half-wave, the full-wave bridge rectifiers, and we said that a half-wave rectifier uses only one diode. So that's the advantage. Which type of rectifier circuit uses 2 diodes and a center-tapped transformer? So let's dissect this question a little bit. So they're asking us for which rectifier circuit. So is it half-wave, full-wave, bridge rectifier? Those are the 3 types that we learned. So which rectifier circuit? So it's one of those, right? But they're asking us about one that uses 2 diodes, as well as a center-tapped transformer. So that was the full-wave rectifier. Remember, a bridge rectifier uses 4 diodes without a center-tapped transformer, right? So the answer to this question is full-wave. Next question in the question pool. What is the output waveform of an unfiltered full-wave rectifier connected to a resistive load? All right, let's dissect this question a little bit. they're asking us about what does the output waveform look like. All right, so it's output waveform. What does it look like? And it's an unfiltered full wave rectifier, not half wave rectifier. And they're just putting this part in maybe to, seem sophisticated or confuse us, but they're saying that it's connected to a resistive load, okay? So full wave rectifier, we said that half wave rectifiers will have the same frequency as the AC, but we said a full wave will have twice that amount. So the answer for a full wave rectifier, the waveform will be a series of DC pulses at twice the frequency of the AC input. If you recall, for a half wave, it's the same, but for a full wave, it's twice the frequency of the AC input. Moving right along. Which of the following components are used in a power supply filter network? Okay, so let's dissect this question. They're asking us about components, so the answers will give us some components. Things like resistors, transistors, capacitors, inductors, those are the components, switches and so on. So the answer will be a list of components. Which of the following components are used in a power supply filter network? So when we looked at filter networks, we saw that there were two main components that comprise them, and that's the L and the C, or the inductor and the capacitor. So that's the answer. Capacitors and inductors form a filter network in a power supply. Moving right along. What useful feature does a power supply bleeder resistor provide? So let's dissect this question. So what useful feature, in other words, what purpose does a bleed resistor in a power supply? What's the purpose of a bleed resistor or bleeder resistor? Well, last class we gave the reason for it. We said that it ensures that the filter capacitors are discharged when power is removed. We don't want it to be live and dangerous even when we switch off and unplug. So the bleed resistor, if you recall, is in the circuit, and it's such a high value that it doesn't affect the circuit normal performance, but when it's switched off and not in use, it will quickly or slowly drain away that extra energy in the capacitor, so it's no longer dangerous. Next question in the question pool. Which of the following is an advantage of a switch mode power supply as compared to a linear power supply? So let's dissect this question. So they're asking us about an advantage. But an advantage of what? A switching power supply versus a linear power supply. And we said, remember, we said the switch mode power supply is much smaller than the equivalent linear power supply. We said the linear power supply uses a big clunky transformer. Well, the reason why, or the advantage of a switch mode power supply over a linear power supply, is that high frequency operation allows the use of smaller components. So that's the advantage, and that's why we had it on the slide deck. Okay. So here now we have a diagram that will be used for a few questions. So this is a circuit diagram. It should look very familiar to you. It was in the slide deck, and we pulled out some components that were numbered, number 1, number 2, number 3, and so on and so on. And we pulled out a couple of components and we gave them names. So that's the basis of the next set of questions. So in the exam, you'll have that diagram, and they will ask you questions like this. Which symbol in figure G7-1, so let's see, this diagram here is figure G7-1. Right, so they're asking us which symbol in figure G7-1, that's the diagram above, or the circuit diagram above, represents a field effect transistor, or FET. So we just need to look at the diagram to see which one is the FET. Is it this? No, it's not. This is a transistor. Is it this one? No, it's not. It's a Zener diode. Is this? No, this is a varactor diode. Ah, here we are. This looks like an FET, or field effect transistor. And therefore, we see the number that's next to the symbol is the number 1. So therefore, this is symbol 1, and that's the answer. Which symbol represents a field effect transistor? Symbol number 1. It's as straightforward as that. So we have a series of questions like that. So let's move quickly. Which symbol in figure G7-1 represents a Zener diode? So we're looking for a Zener diode. Is it this one? No, it's not. Is it this one? No, it's not. What about this? No, that's a regular diode. But we look up here and we see that symbol number 5 is the symbol for a Zener diode. There we have the number 5, and here is the answer to the question, symbol number 5. Next question. Which symbol in figure G7-1 represents an NPN junction transistor? So we're looking for transistor. Quickly we identify, here's our trusty little transistor, and it's symbol number 2, and that's the answer. Symbol 2. Let's go again. Which symbol in figure G7-1 represents a solid core transformer? So we're looking for a solid core transformer. All right, where is our solid core transformer? Is it this? No, it's not. That's a center tap. That's a tapped inductor. Is it this? No, that's a resistor. Is it this? No, that's a capacitor. Here we go. That's it right there. It's an iron core transformer or solid core transformer. And that is symbol number 6. So that's our answer, symbol 6. Next question in the question pool. Which symbol in figure G7-1 represents a tapped inductor? So let's look for, well, we just said it in our previous question. So let's go straight to it. Tapped inductor. Here it is, our tapped inductor. What symbol is it? Symbol number 7. And that's the answer here to that question, symbol 7. Moving right along. Next question in the question pool. Okay. Which of the following describes the function of a 2-input AND gate? So let's dissect that question a little bit. So what are they asking about is the function. How does it work? You have some inputs, you have some outputs. So how does that work? Well, it's a 2-input AND gate, and last class we did the truth table for it, and we noted that the output is high or 1 when both inputs are high. Remember, we used the avocado as the example, and we said our mouth will only open to eat the avocado when our both hands have avocados in them. So that's the AND gate. It will be high or it will be 1 when both inputs are high or 1. Next question, similarly. Which of the following describes the function of a 2-input NOR gate? So what are they asking us about? The function, meaning how it works. We have inputs and outputs for the logic gates. And it's a 2-input, what kind of gate? NOR gate. All right, and we learned that that type of gate, the NOR gate, is low when either or both are high. So that is the answer to this question. If you need a review or refresh, just have a look at the slide deck or the video from the last class. Okay, next question in the question pool. How many states does a 3-bit binary counter have? So let's just dissect this question. How many states? What they're asking is how many possible values can this 3-bit binary counter have? So remember last class we showed all the possible combinations starting from 000, 001, and so on and so on. And we showed that when we went through all of the possible values that a 3-bit binary counter could have, because it could only have a 0 or 1 in each of the 3 positions, there are only 8 states in all, total of 8. So that's the answer. And our last question in the question pool before we go into our theory is, what is a shift register? And we have defined a shift register as a clocked array of circuits that passes data in steps along the array. So again, feel free to review the theory from last class via the slide deck or the video. Okay, so we go now into the theory for today's class. And we are now dealing with oscillators. We have come across oscillators before in the technician class, and we would have come across a bit already in the general class. So what is an oscillator? An oscillator is a circuit, because we've been dealing with circuits. That's what we're about. But it's a circuit that generates an AC output or a sine wave, right? Remember what a sine wave looks like? Nice smooth wave like this. This is our sine wave here. It generates a sine wave. And the usual components, we have an amplifier. So this is our symbol for an amplifier here. We have the input, it goes through an amplifier, and then we have the output, which is a sine wave. And the output is fed back through a filter to the input. So if you look at it here, you have the input, the amplifier, it amplifies it with an output, but notice part of the output goes back to the input, and that is called feedback. But note that it passes through a filter. So there's a filter that the feedback goes through. And that filter inside of there is what determines the frequency of oscillation. So that is what an oscillator from a block diagram perspective looks like, and you need to know this for your exam. The filter determines the frequency of the oscillator. Now there's a type of oscillator that's called the LC oscillator. So you might be thinking, wait a minute, L and C, that sounds very familiar, and you would be quite correct. L for inductor, C for capacitor. So that's exactly what an LC oscillator is. It uses an inductor and a capacitor. They tell us right here, LC oscillator. And we know that an L is inductor, and we know that C is capacitor. So that's exactly what an LC oscillator is. Inductor, capacitor, oscillator. And together, the inductor and capacitor forms what you call a tank circuit. All right, so if we were to look at the diagram here, here's our trusty inductor, our trusty capacitor, and this circuit here is referred to as a tank circuit, and the feedback goes through for our oscillator through the tank circuit. So very similar to the previous diagram, but just that we broke out the block diagram and showed you a little bit of the guts, a little bit of the inside of the block diagram. Now the tank circuit, which is remember, the inductor L and the capacitor C, this is the filter that determines the frequency of the oscillator or the frequency of oscillation. So if you got a question asking you, what determines the frequency of oscillation in an LC oscillator? Well, it's exactly that, the tank circuit, and it's a filter. And that is what determines the frequency, the value of the inductor and the value of the capacitor. So we come to now amplifiers, and we dealt with amplifiers before, but now we are going to talk a bit about the different types or classes of amplifier. Yes, we have classes of amplifier. All right, so one class is called the Class A amplifier, and another class is called the Class B amplifier. And you're probably thinking, all right, the next one is probably called the Class C. Yes, that is correct. But we also have another class of amplifier called the AB amplifier. And then the Class C, and then there's the Class D. And there are actually several other classes as well. So we're just illustrating that there are different classes of amplifier. Each class, just like a fire extinguisher, you know, you have a Class A, Class B, a Class C extinguisher, and they use for different types of fires. So just like you have different classes of fire extinguishers, you have different classes of amplifiers. And each class represents a particular property. So we say here that the Class A amplifier is a linear amplifier that has high gain and very little distortion with a Class A amplifier. So that the output is very close or similar to the input. Very little distortion, except that the output is larger than the input. That's why it's called an amplifier, because it amplifies. And it's very suitable, of course, for CW, AM, and SSB phone signals. So that's the Class A amplifier. So just take it for granted for now there's something called the Class B amplifier. Take it also for granted that we have something called the Class AB amplifier. But let's discuss now the Class C amplifier. The Class C amplifier, notice we said that the Class A amplifier was linear. Notice that the Class C amplifier is not linear. And we're saying here that it is suitable for amplifying FM and CW. Note that you don't need linear for these, right? As above before, we saw that the Class A amplifier is good for AM and SSB phone signals. The Class C amplifier is suitable for FM and CW signals. And we note here that Class C amplifiers are more efficient than all the other classes of amplifiers that we have listed before, which is A, B, and AB. Okay, so this point here you need to know for your exam that Class C is not linear and it's used for FM and CW and it's more efficient than the other classes. Just for your information, we like to give a little something extra in the class. You don't need to know this for your exam. However, here are the diagrams that show you the circuits for a Class C amplifier, for a Class B, for a Class AB, a Class C, and even a Class D. So these are what the actual circuits look like. Not that you need to learn it for the exams, but you know, some persons are a little more advanced in electronics like to know, you know, what are the components? How can you tell the difference? And even if not, just have a look at it to see that and convince yourself that they are quite different, in fact, in terms of the circuitry between A, B, AB, C, and D. Okay, so of course, as hams, we're always trying to be more efficient. Why? Because, you know, we always want to use only as much power that we need to use. No more power. That will save us in our electricity bill. It will also help us in emergency communications where we may not have line power operating out of battery, and we want to be very efficient so we could run for as long as possible. Imagine in a disaster, you have to run for a long time, and therefore you need your equipment to be very efficient. Yes, indeed. So how do we discuss efficiency when it comes to amateur radio? Well, one of the ways is to look at RF amplifier efficiency. So notice we had said earlier that Class C amplifiers are more efficient than Class A, Class B, Class AB, and so on, right? So how do we determine what efficiency is, or how is it calculated? Well, we say here that efficiency of an RF, meaning radio frequency amplifier, is calculated by dividing the radio frequency output power by the DC, or direct current input power. So at the bottom here, we have a diagram show you we have a power supply. It's plugged into the wall. It's delivering DC power into our radio, into our transmitter. And the transmitter is delivering RF, or radio frequency power, to the antenna. So therefore, let's say this output power is 50 watts or something like that. And let's say this input power is, let's say, 100 watts. So you can have an input power of one value and you have an output power of another value. And when you divide them, you put the RF output power in watts divided by the DC input in watts, and you get the efficiency. So that's how you calculate efficiency for RF. So at this time, we will take a short break, take a stretch, have a bathroom break, and have some water, and we'll meet you back in approximately 2 minutes time. Okay, welcome back. And during the break, we did have a question from a participant asking about the crystal oscillator, and you're quite correct. There are oscillators that use crystals to generate. So you have quartz crystals. So we will come a little later on to show where the crystal oscillator comes in. Thank you very much. Excellent question indeed, Shafina. So as we continue, there's another concept that we need to be aware of in circuits, especially in power amplifier circuits, and that is the concept of self-oscillation. But what is self-oscillation? It can occur in power amplifiers due to the feedback caused by stray capacitance. Remember, we said a couple of classes ago that a lot of components, a lot of circuits are not perfect in their own. So stray capacitance or parasitic capacitance or extra capacitance or unwanted capacitance can cause self-oscillation to occur. But guess what? There's a solution to self-oscillation. And that solution is to eliminate or neutralize the self-oscillation. And to do so, we induce or introduce or we add some feedback that is out of phase with that stray capacitance. So if you were to look at our diagram, you will see that we have added some capacitance here out of phase with whatever stray capacitance may occur in the circuit. So introducing that extra capacitance eliminates or neutralizes the effect of the parasitic or stray capacitance that the circuit may very well have as a result of the other components inside of there. So it's there and we can do something about it, and that is called neutralizing. Okay, so we have dealt with filter circuits before, and if we were to look on the left-hand side of our diagram, we will see that we have put up 4 different types of filter circuits, right? But filter circuits are actually found in amateur radio equipment, and they're very important. If you were to look at the circuit diagrams, or you were to open up a radio or transceiver, you will see many stages that involve filter circuits. And as we come to other circuits in this evening's class, we will see the use of filters and filter circuits for different uses. But one of the use for filters or filter circuits is to clarify or to process radio signals. We can do that with filters. So on the left-hand side here, you will see 4 different types of filter circuits. You have the type that will be a low-pass filter. We have a high-pass, we have the band-pass, and we have the band-stop. And these circuits really are the diagrams that show graphically how or the effect of the circuit. It's not the actual circuit themselves, it's just a diagram to show you a graph really what happens with each type of filter circuit. So on the right hand side here we have expanded the low pass filter. So that's what that means. We have the 4 types here up on the screen, but we are right now dealing with the low pass filter. So the low pass filter, what it does, it passes all of the signals or all of the frequencies below a certain value. And that value below which it passes is called the cutoff frequency. And everything above that, it reduces or it attenuates. So for example, from this frequency all the way up to this frequency here on our diagram, our low pass filter will allow it. So it passes these frequencies. And as it comes to this point called the cutoff frequency, it rejects. Now, the cutoff point or the cutoff frequency, the level of that signal is approximately half of the main signal. So you just need to know that half is also represented by a drop by 3 dB or minus 3 dB. You may recall when we did the decibels and we said that negative 3 dB represents half of the signal. So that is exactly what we also mean here. Our filter, when it gets to the point of dropping off half of the signal, that is the cutoff frequency. Anything below that, it permits, and anything above that, it rejects. Okay, so in respect of our filter, we need to be aware when we introduce a filter into operation, either into a circuit or into our amateur radio use, we need to be aware of impedances. Remember we said that hams are matchmakers. So just look at the diagram below for a moment. We will have an electrical outlet. We plug our power supply in to get DC power output. Our DC power powers our transceiver or radio. And then our radio would normally go to the antenna. Now this is an HF transceiver, high frequency transceiver, high frequency radio, and we have a high frequency antenna. But we have introduced something into the feed line. So between our radio and our antenna, normally we go straight to the antenna. We can have other components inside of the other devices, but we have just introduced something called a low pass filter. So we need to ensure, because our transmission line has a certain impedance, and we said hams are matchmakers, because we use 50 ohm impedance transmission line, when we insert a device such as a low pass filter, we need to make sure that the input impedance and the output impedance are also either 50 ohms or pretty close to. We need to match the impedance. So remember, we keep saying that hams are matchmakers. So therefore, that's an important factor when we introduce things like low pass filters into the circuit. We need to make sure input and output impedances are similar or about the same. So one of the uses of the low pass filter is to block VHF and UHF harmonics produced by an amateur HF transceiver from reaching the antenna. What do we mean by that? So this is an HF transceiver. It's producing an HF frequency that we need to get to the antenna to communicate to an amateur radio operator around the world. But our transceiver or stages there will produce harmonics. And if you recall from the technician class, we say harmonics are multiples of the fundamental frequency. So whatever frequency we produce on our radio, we do have multiples of it being generated called harmonics. And those are much higher in frequency. So we introduce a low pass filter to pass our frequency that we want, which is the HF frequency, and to attenuate or to reduce or to drop off or to eliminate the high frequencies that would otherwise be transmitting. So that's one of the uses of a low pass frequency, to allow the intended frequency and to eliminate the harmonics from reaching the antenna. So the input of the filter is connected to the output of the transceiver. We see that here. This is the input or the in of the filter, and this is the out. But the input of the filter is connected to the output of our radio or transceiver. And the output of the filter is connected to the antenna. So this is our output from the filter, and it goes via feed line or cable to our antenna. Now, the last bullet point says what we said a short while ago, which is, since the low pass filter becomes part of your antenna system, the input and output impedances need to be about the same as the transmission line. Okay? So 50 ohm transmission line, therefore you want the input impedance and the output impedance to be about 50 ohms. The actual value will not be in the exam. They'll just expect you to know that when you introduce it, the input and output impedances need to be about the same. So we come to another type of filter called the band pass filter. So if you recall, we had 4 types of filters that we were looking at. The diagram that shows the low pass filter, how it looks on a graph. We did the high pass filter, we did the band stop. But we are now going to go into a bit more detail on the band pass filter. So for the technician class, we need to know about the low pass filter and we need to know about the band pass filter. So we are now expanding the band pass filter into this diagram here. And we'll notice that the band pass filter will reject these frequencies and then start to allow these frequencies, and then again it starts to reject. So that's why we call it a band pass. Only part of the band passes. It drops off or attenuates frequencies up to this point. It allows these frequencies and then it stops the frequencies above it. So this is called a band pass filter. So it allows a range of frequencies, let's say frequency 1 to frequency 2, and all of the frequencies in between to pass while rejecting frequencies lower and frequencies higher, or frequencies outside of the pass range. So this is what the graph of the band pass filter looks like. The range of frequencies that are allowed to pass is called the pass band. So from frequency F1 to frequency F2, This is called the pass band. The width of the range is the difference between the two frequencies, frequency 1 and frequency 2. Now, notice that the point at which frequency 1 is and a point at which frequency 2 is where the filter starts to reject half of the signal. So if it's rejecting half of the signal all here, or less than half, it's rejecting, and then all of a sudden you reach about half, it starts to allow. So the point at which it starts to allow and the point at which it starts to drop off to about half, that's the range that we are referring to, or those are the frequencies. So again, notice the 3 dB, still 3 dB half. Again, you recall that from doing decibels and the importance of knowing that 3 dB represents half of the power. So when we look at the difference between the upper limit and the lower limit, frequency 1 and frequency 2, we refer to it as the bandwidth as well. So this will come in your exam, and hence the reason we are looking at it, the bandpass filter. Another couple important items to discuss when we deal with filters is ultimate rejection. And no, that's not when you get blank. It's a parameter, it's a feature of filters, ultimate rejection. And the other one is insertion loss. Anytime we put something into a circuit, there is some loss likely to be associated. So for filters, the same thing. When you insert your filter, you have that loss. So let's discuss ultimate rejection. It is a term used to specify the filter's maximum ability to reject signals outside of the passband. Okay, so that's what the definition of ultimate rejection is. Maximum ability. So it is the ultimate ability to reject signals. That's what a filter does. They reject. Filters, of course, are not perfect. So when we insert them into the circuit, they also attenuate or reduce the input signal. So we need to become quite comfortable with some of these terms. Attenuate simply means reduce the input signal. So to some extent, it will reduce. And therefore, bear in mind that it reduces the signal of the unwanted parts, and it also reduces the signals of the wanted parts. So it reduces the signal. Once you insert that filter into the circuit, it will reduce your signal to some extent, or it will attenuate. The property, or we call that when we use a filter in that way, and it reduces or it attenuates the signal, we refer to that as insertion loss. So think of it as that we have just inserted the filter, and there's loss of signal by inserting it, and therefore, hence the term insertion loss. All right, so we also use filters in transmitters. So the first point that we make here is that filters are also used in amateur radio transmitters. So you will find them in various stages. You'll find them in various circuits within transceivers or radio equipment. One of the uses of filters is to produce a single sideband or SSB signal. Again, in the technician class, we went through what SSB was, so we'll just touch it very lightly here. In the circuitry, we have what is called a balanced modulator. It's also referred to a mixer. Sometimes they call it a balanced mixer. And that balanced modulator is used to combine the audio signal with a carrier signal that is produced by an oscillator. So if we were to look at the diagram just below here, we will see our trusty balanced modulator, also known as a mixer. And that is taking an audio signal or an audio frequency. Notice it says microphone here, AF amplifier, and so on. So this is an audio signal that is going into the balanced modulator. The RF signal that's produced by the oscillator or the carrier signal also goes into the balanced modulator. So that's why they say that the balanced modulator, also called a mixer, combines the audio frequency with the carrier or RF frequency. So that's the purpose of the balanced modulator. And the resultant output of the balanced modulator, in other words, this balanced modulator here takes the audio frequency and the carrier frequency and mixes it. And what it produces is called the output that contains both upper and lower sidebands. But note, it does not contain the carrier. So it's only the upper and lower sidebands that come out from the balanced modulator or the mixer. And if you want single sideband, so remember upper sideband and lower sideband on the left-hand side here, we see we have the carrier, we have lower sideband, we have upper sideband. Our balanced modulator is only producing lower sideband and upper sideband. But when we use a radio, we don't want to use both sidebands. In amateur radio, we either want to use lower sideband, LSB, or upper sideband, USB. And to do that, this balanced modulator here will give us both of the upper and lower sideband. So we get in lower sideband and upper sideband. So to get single sideband, which is either upper sideband or lower sideband, we need to filter out the sideband that we don't want. So therefore, we have this filter or sideband filter that filters out one of the sidebands. It either filters out the lower sideband if we're operating in upper sideband mode, or if we want to operate in lower sideband mode, it will filter out the upper sideband. And that's what the sideband filter stage of the circuit does. And that's why we see filters are also used in amateur radio transmitters, because we are seeing here that the filter is used to take the double sideband or the upper and lower sideband and just filter it out and leave you with either lower or upper sideband only, so that you could operate SSB, single sideband. We now come to receiver circuits. So the first type of receiver circuit that we will deal with, and we did talk about this already in the technician class, but we go a little bit more into detail. It's called the Superheterodyne Receiver, or sometimes just called the Superhet Receiver. That receiver is very popular for use in AM, CW, and SSB receivers. So again, it's the Superhet Receiver for AM, CW, and SSB. Notice we did not say FM, because we'll come to the type of circuit for FM later. Superhet receivers convert the received signal, that's the incoming signal on your receiver, via the RF amplifier to an intermediate frequency, or IF. So anytime you hear the term IF, it's not the word if, it's intermediate frequency. And that's what a superhet receiver does. It converts the incoming frequency that the other radio operator is transmitting to you on, and it converts that to an intermediate frequency. And the circuit that is used to convert from that received signal to the IF is called a mixer. If we were to look at our diagram here, we'll see our antenna. We're receiving our radio transmission, and from the RF stage, it goes to the mixer. And that mixer is what produces the signal for the IF, or intermediate frequency. So we have some extra information here for those who are interested to see what the various signals look like at the various stages in the superhet circuit. Now the mixer, the same mixer that we're looking at here in our diagram, it takes the incoming signal, yes, together with one produced by a local oscillator called the HF oscillator, and then it produces that IF signal. So that's what the mixer does. The mixer takes the incoming signal and mixes it with a frequency generated locally via the local oscillator, and that mixer outputs the IF signal, or the intermediate frequency signal. So that's why these block diagrams are so very useful. And again, we have what the waveforms look like here in case you're interested. We note here that in some single sideband receivers, there is a circuit called the detector, or product detector, that demodulates the IF signal to go to the audio frequency stage. All right. We'll repeat this point in a bit, or look at it from a different perspective. So we're still under superhet receivers, or superheterodyne receivers, and we're saying it's good for AM, CW, and SSB type modulation. And another point here about the product detector, it is used to combine signals from the IF amplifier. Remember, we were going through in stages here. Now this is kind of all about stages, you know, it's similar to, let's say we're breaking a bread. You know, we have to get the ingredients, we have to mix it up, we have to let it rise. We have to then put it to bake, then we let it cool, we cut it up, and maybe we might combine it with some butter, and then we eat it. So that's what our block diagrams are showing us here, really, the different stages of signal processing. Just the same way that you'll bake a bread using different stages, we will also receive a radio signal and process it in different stages as well. So each stage here. So we're at the point where we are talking about the product detector here. The product detector takes the signal from the IF stage or the intermediate frequency stage, and it uses another local oscillator called the BFO or the beat frequency oscillator. And it takes that signal, combines it with the IF signal, and it sends it to the audio. So that is exactly how a receiver works. And if you think about it, so you turn your radio on, your handy HF transceiver, and you're listening to your amateur radio colleague talking. It's coming through the RF stage. It's being mixed with the local oscillator. It goes to an IF frequency. That frequency then has a detector that mixes it with a BFO. And next thing you have your audio, and you're listening to the amateur radio operator. And this is the block diagram of a superheterodyne receiver. And note that in the simplest combination for a superheterodyne receiver, you have the three stages: the HF oscillator, or sometimes called the local oscillator, the mixer, and the detector. So those are, and it's a question in the question pool. They'll ask you, what is the simplest combination of stages when you're constructing a superhet receiver? And these are them. And they are highlighted in yellow here for you on the diagram. You have the HF oscillator, or sometimes called the local oscillator. You have the mixer, and then you have the product detector. So we have been dealing with AM, CW, SSB type receivers. But FM receivers are quite different. So forgetting amateur radio for a moment, you know, on your broadcast radio, you have the AM band and the FM band and so on. And you ever notice the difference in the sound of AM when there used to be a lot of AM radio stations versus the FM. So the FM receiver is quite different. It uses different circuitry compared to the superhet or the superheterodyne receivers that we just did. And we noted that the superhet is designed for AM, CW, and SSB reception. However, for FM receivers, we use a different circuit. And in the FM circuit, we'll notice here very similar stages to the AM, but notice that in the case of the FM, the detector is actually called a discriminator. So that's an important point. It will be in your exam that the discriminator is an important stage in FM receivers. You will not find it in the AM, CW, or the SSB receiver type circuits. It's for the FM type of circuit. And that discriminator is used to convert the IF into the AF. So remember, just like before, we go in from the radio frequency to an intermediate frequency, and then we ended up with AF or audio frequency, which is what we listen to. That's what's coming through the speaker. So radio waves coming into your receiver, and you are converting it into audio frequency. That's why we have all of these stages of the various receivers. And for the FM, we use the discriminator. So let's modernize things a little bit. So of course, in today's world, we find that transceivers or receivers or transmitter equipment uses something called direct digital synthesizer, or DDS, to control the receive and transmit frequencies. So modern transceivers use DDS. Now, DDS uses high stability variable frequency oscillators, and that gives much more stability than receivers that use the older analog type local oscillators. All right, so note that that's one of the advantages of the DDS. It allows for variable frequency selection with the stability of a crystal oscillator. So remember, the participant who mentioned the use of crystal oscillator was quite right. So we are talking here about DDS, direct digital synthesizer type circuits, which are used in modern equipment. And to modernize a little further, we now come to the concept of SDR, or software-defined radio. So we have had a lot of advances in the digital techniques over the years, and we have been able to get very effective at generating and receiving radio signals using these digital techniques. So many transceivers today on the market implement most of the signal processing function using DSP, digital signal processors, and software. So that radio that we have now has been modernized to use digital techniques to do all of the processing in software. So that term that we use to describe when we're using software and digital processing inside of radios or transceivers, that equipment is referred to as SDR, or software-defined radio. And we have some diagrams here that shows what the software-defined radio from a block diagram standpoint, as well as what the waveforms would look like. You don't need to know this for your exam, but this is a little bit extra to show you the various stages where you have analog to digital conversion and digital to analog conversions and so on. All right, so the detail is not really necessary. We'll point out the areas that you need to learn for the exam. Okay, so speaking of software-defined radio, how does it work? Well, it uses two signals for modulation and demodulation. So note that those two signals are 90 degrees out of phase. So that is an important point that you need to learn for your exam, that for SDR, or for software-defined radios, there are two signals that are used, and both of them are 90 degrees out of phase with each other. And the first signal is called the I signal, and the other one is called the Q. So you have I and Q. Those are the two signals that are used for SDR. Now, when an SDR is receiving, the receiver's analog or ADC, analog to digital converter, converts the incoming signal into a series of values, and those values represent the I and Q signals. The opposite occurs when it's transmitting. When the SDR is transmitting, it does the reverse and uses digital representations of the I and Q signal to produce an RF output. So we have a simple diagram on the right-hand side here that shows that where you have your antenna and you have your analog to digital conversion and your digital to analog conversion, depending on whether you're receiving coming in or you're transmitting going out. And note that one of the advantages of using the I and Q signals for SDRs, or software-defined radios, is that you can use all types of modulation and create all types of modulation and receive all types of modulation just in software. You don't have to go and change the hardware and change the components to do a different mode. You can just update the firmware and just tell the equipment, do this mode, and it will do it because it's software defined. You just need the appropriate code to be able to generate. So that's why it's called software defined radio. Very much the in thing in amateur radio, state of the art at the moment. So folks, we have come to the end of this evening's session. Just for anyone who missed last week's virtual panel discussion, there's a link to the video recording, and highly encourage persons to take a look at it. Besides the course that you're doing as an amateur radio operator to prepare you to take the exam, of course, other educational information can be helpful. Other sessions, continuing education is very helpful, and the panel discussion can help you come to terms with some of the practicalities of what you're learning right now from a theoretical standpoint. So encourage persons to take a look at that recording just in case you missed last session. Of course, we continue to invite persons in the course to check out Zello. It's a voice over IP app. Just remember, it uses the internet, but it does give you a good idea of radio operations. And as React, we use all forms of communication that's legal, and Zello is one of those. And we're inviting persons in the course to consider joining Zello. And these are the two channels that we use on Zello. One is the primary, one is the secondary or backup, and we'll be switching very soon. So check out Zello. Certainly like to thank everyone for participating. Please do continue to review any of the videos you might have missed. Anyone who is just joining the class, you would do well to check out the technician class course that we ran last year. All of the videos are available as on-demand playlists via this link, tech.ttreact.com. Also, remember that each person is getting an email and an SMS text at this point per week. Also, if you're not getting any of those messages, please let me know. Of course, in TNT, we still continue to have our COVID-19 cases pretty high still. We're seeing some, possible positive signs, but, too many deaths as well. And it's, we have to do all that we can. We're still under state of emergency with curfew. We're asking everyone to be safe out there. Note that we are now in the hurricane season, and we, of course, are having our tropical wave weather associated at this time in Trinidad and Tobago. So our next session, we expect to have next week, Friday, God's willing, Friday, the 11th of June, 2021. Usual start time, 8:30 p.m. So I do look forward to meeting up each and every one of you. So do take good care of yourselves, be safe, and do have a good night. Thank you. Okay, Sylvester, thanks a lot, man. Good night to you as well. Larry, good night. Sure, no problem. And probably give me about 10 minutes or so, and you can give me a buzz. Sure. Okay, Adish, take good care. Do have a good night, man. Yeah, be safe as well. And thanks for that great question there, Shafina. Well done. Jessica, good night. Roger, good night. George, good night as well. Natasha, good night. Yeah, okay. Charlene, good night as well. Okay, Bob, good night. God blessings to you as well. Yeah, hope you keep safe too as well there, Jessica. And have a good night, George. Okay, Larry, take good care, man. Gary, have a good night as well. Yes, okay. Good point. Riverine flooding yellow alert also issued. Thanks so much there, Gary. So everyone has to be careful, be safe. Kevin, have a good night as well too. Roger, good night to you as well. Thanks a lot, George. Will do. You get some rest also. June, do have a good night. You be safe. Okay, Abba, have a good night as well. Great to have you. All right. Okay, cool. All right, got you there, Ramzan. Understood. All right, Desi, glad to have you. Glad you got back in. Jerome, also do have a good night. Eustace, you're certainly welcome. Thank you and have a good night as well. Okay, Ian, yes, you too. Do have a great weekend. Okay, Ramzan, take good care.